In this module, we are going to look into a vector decomposition. Let's assume that this box has a force acting on it by this arrow. This is a force vector. I can imagine that there are actually two forces, the blue one and the orange one, acting upon this crate in such a way that their vector sum is the one that we see before. So this means that now I'm decomposing this vector into two vectors like this. But what I can do also is that I can decompose them into two vectors this way. So now you can see that vector decomposition can be done in an infinite number of ways, so long as when you sum it up, it comes back to what it started with. So the choice of decomposition is actually up to you, but it would make sense to pick the one that makes our life easier. And in this lesson, we are going to learn about decomposition in an orthogonal way. Orthogonal means perpendicular. An example of an orthogonal axis is the famous Cartesian coordinate. You might be familiar with Cartesian coordinate already because you might have already seen the x-axis and the y-axis. And in our understanding, the x-axis and the y-axis are always perpendicular to each other. In 3 dimensions, we also have the z-axis, which are also perpendicular to both the y, the x, and the y-axis. And in this case, the z-axis is perpendicular to your monitor right here. So let's focus on the two-dimensional space first. You will have to define what we call a unit vector for each of these orthogonal axes. For x-axis, it's conventional to call this unit vector I. For y-axis is j, and for z-axis k. So for x-axis, I have the unit vector I drawn here, and for the y-axis, I have a unit vector j drawn there. Now, I have a vx, a vector vx drawn here, and it's this long. I also have a vector vy drawn over here with this long. Now, if you recall, if I sum vx and vy, what I have to do is I have to connect the tail, let's say the tail of vy to the head of vx. So I will have to put vy over here. And then I have to draw from the tail of vx to the head of vy. And this is where I will land. So essentially, you will see that this vector is the summation of vx plus vy. So I can do this, vx plus vy, and if vz exists, I'm going to put it here as well. So the total vector now is going to be decomposed of vx plus vy plus vz. Then let's take a look at each of them individually. We know that a vector is composed of direction and a magnitude, right? So for vx, I have direction I, and I will have a length of the magnitude of this vector vx right here. Similarly, I can do that for y. Vy is going to be composed of the direction and the magnitude, and likewise for vz. Now, what would be the magnitude of the vector v? In 2 dimensions, it's going to be composed of vx and vy in vectors, right? And we have drawn the triangle for the summation of these vectors, and we know that these guys are perpendicular, So therefore, the length of this guy can be calculated using the Pythagorean theorem. So in two-dimensional case, I'm going to have the magnitude of v equal to vx squared plus vy squared and square root. And if I have vz, I'm going to have to add the magnitude of z component as well. And therefore, oops, mistakes here. And therefore, the magnitude of the vector v is going to be in this form. These three equations are quite useful. In the case that you know the vector v and you want to find the magnitude in the x direction, what you have to do is you take a dot product of that vector v with the unit vector I. Similarly, if you want to know the magnitude in the y direction, you take that vector and make a dot product with the unit vector j. And so is the magnitude in the z direction. It's going to be equal to the dot product of vector v and the unit vector k. And this is valid because we have chosen an orthogonal decomposition. Orthogonality between I, j, and k make these equations valid. Let's take a look at this in detail in the next module. To enforce your learning, write, comment, or share what you have learned today and hashtag PhysicsLitUp. And subscribe to Physics Lit Up for the next video.